Okay, so it says live. I think people should be able to join.
Fabulous. I know it's
Uh,
always fun the first time.
Right. As this recording has started. Okay, so that should be good.
Also, Dr. Taylor, it's nice to meet you. I'm Madison. I'm one of the new coordinators here.
Wonderful. Nice to officially meet you, Madison.
Hi.
Wonderful.
Nice to meet you.
Hi,
Yeah,
I'm
okay. It
Chris.
seems that people are pouring in, I think. Well, there's 10 right now. Um, so yeah, Chris, have you done one of these before? I don't
No,
remember.
I have not.
Okay, so you're gonna be passing questions, which is easy. All you do is you see the Q&A button at the top.
Yes.
So they will be able to create posts and ask questions for Dr. Taylor. And then if there's anything like inappropriate, I think you hit like little three dots and you should be able to get rid of it.
Okay.
That's all you have to do. Is just make sure they're not saying anything stupid. And then I'll
Okay.
be the one whenever she asks questions, ask for questions to read it out to her. And that's literally it. And then Madison's just here to oversee.
Okay.
Alrighty.
Fabulous. And I will, I always have the intention of asking for questions like every half hour on the half hour. That almost never happens. So I always have great intentions of doing it in a way that is predictable
Mm-hmm.
and easy to foresee. And then what often happens is I will do like a really long math problem and I'll be like, let's just check in with everybody
Right. There's
after
probably some
that, shall
questions
we?
after that. Mm-hmm.
Um, but every once in so I will try to be predictable, but I have to admit I think I fail at that most of the time.
Oh, it's okay. It's okay.
So but but hey, um it's 3 o'clock. Is it that time?
Great.
It seems so. People are coming in. So,
Perfect. Okay. Did y'all want to introduce or do you want me to introduce and get started? What's the plan?
I mean, I think you can go ahead and introduce. I think that's
Yes.
'cause they don't really know who
Um,
we are.
that's fine. That's the thing. We feel bad for like the wonderful voices behind the scenes besides me.
Right.
All right. All right, well, it is 3 o'clock. We'll go ahead and get started. So we are going to do a exam review for exam one. This is also hosted by the wonderful Living Learning community. So if you hear other voices, that is them. They are also the fabulous people that make this event run smoothly. As somebody who did actually try to help Dr. Deekman when we ran exams online during lockdown, I am very grateful for these other people because I have tried to do their job before and it's a lot. So great, very, very grateful. So we're going to talk about exam one. We'll also talk a little bit about general exam things since this is the very first exam. So we're going to basically do a little bit of where is some of the stuff to look at. So one of the things I have up on the screen right now says exam one content. So it says chapter 13, solutions, all sections except 13.7, which is colloids. So colloids are really neat. They're really fun. I usually still include slides on them because I think they're neat, but we don't test on them. So that is one of those games where like, if you care about them, you can always ask, but I will start off with like, not on the exam. And then Henry's law, won't do any calculations on Henry's law, but the concept is fine. And we could definitely talk about what that concept actually is. Chapter 14, kinetics, we're sections 14.1 through 14.5. This is most of the chapter and does basically run all the way, including integrated rate laws and half-lives. So there are a few things that we basically save for exam two, but this is most of that. The other thing with this is, I don't know if y'all can see it, I know it's a lot smaller, but it says posted on Friday, February 7th. So what I am going to do is click over to e-learning. And I know that this is small. I'll try to make it a little better, but whoopsies, not that big. sorry, the thing I always want to be able to show off is this lovely little board on the side. So this is in the 701 section. So all students have access to the 701 section. It's referred to as the exam section. And the instructor team often posts things to the 701 section. So that way we know that every student, no matter what section you're in, has access to it. So this is actually where information about the exam typically goes out through, just because that way, if you're in my 9 a.m. section, or if you're in Dr. Diekman's 1 p.m. section, like, it doesn't matter. Everybody gets the same announcements at the same time. So included in here, I just posted this update about end of chapter questions for chapter 14, because I got asked in class this morning if we give an updated list. So I did those like a half an hour ago as I was getting ready for this. Also, again, information about exam reviews, which this is one of them. This is being recorded, by the way, and that will go up basically as soon as it's ready. Living and Learning Community does a really great job of posting it, and then they send it to me, and then I just check my email in time to post it. On the course homepage, there is information like exam reviews, exam blanks from the spring 2024 semester, end of chapter questions. This one I did just put up. The SI schedule is here. So if you were looking for some other people to talk about chemistry with, there's that too. And if you haven't checked on this big red folder here, this thing says potentially useful information sheet and periodic table. We do provide equations, and I know that this is too small, which is why I also have it over here. So we do provide both constants and equations for the exam. So basically every single exam booklet has not just the questions that we're asking you, but it also has what we refer to as potentially useful information. And that does also include equations. So these are on there. And again, you have access to this PDF file through the 701 section. It's in that red link, as well as a periodic table. It will be full-sized. So all of this stuff is available for you. I would highly encourage y'all to start using this, because sometimes the game with solving a problem is knowing where all of your tools are. So I will be clicking back and forth to this as we have different discussions, just so you can kind of see what is posted on here, what is not. The other thing to keep in mind is this does say potentially useful information. So for example, we still have on here the definition of 1 AMU. That's an atomic mass unit, and its definition to the gram there on the top right. That's useful in Gen Chem 1. I have not seen us ever use that in Gen Chem 2, but it's there. So just to be aware that this does have extra information on it. So it oftentimes has things that you do need, but just do realize that there's too much information on this page. Another good example of that is this table here in the middle that has a list of 5 different solvents and their boiling points, their KB constants, their freezing points, and their KF constants. You will not need all 5 of those solvents. No. But you might need one of them, you might need 2 of them, and honestly, that is the table from your textbook. So instead of choosing the ones that are on the exam, we just grabbed the entire table from your textbook. Also, in case you're curious, I succumbed and I have a Dr. Pepper blackberry soda. So if you see me make a weird face, it's because that is different. That is a fruity, odd thing. Anyway, so do take a look at this. Do become familiar with this, because again, there are actually too many things here. You do not actually need all of them. Okay, one other thing for those of you I did get this question a couple different ways. We will have, I'm going to make this larger in just a minute, coming soon. So they are not ready yet. Room assignments. So what we actually do for this is we assign rooms for the exam, which is this Saturday at 10 a.m. By last name. So again, there are 4 different sections of general chemistry. There are somewhere between 900 and 1,000 of y'all in total. And so we will be in 10 to 12 different rooms around campus, and which room exactly y'all are in is coming. I do not actually have that information right now. To be honest, that's part of the reason why I was flipping back to e-learning, because as soon as it is ready, it'll be posted right here, or it'll be part of this big red folder that says S25 exam information. So just in the off chance that Dr. Diekman had gotten to post it when I hadn't caught it yet, I was double checking. So that will be posted soon. As soon as it's posted, we will announce it all over the place so many times. I did get some questions on, is it the same as last year? No, the registrar does give us some of the same rooms, but not all of the same rooms. And so since we don't have the exact same rooms like we did before, we don't have the same breakdown. Also, due to a variety of different reasons, there's fewer people who take General Chemistry 2 than there were who took Gen Chem 1 with us in the fall. So we basically just start from scratch and redo all the rooms. Well, it's not the only feature. One of those features is the fact that engineers, some of the engineering majors only need 1 semester of general chemistry. So while we very much love our electrical engineers and our mechanical engineers, usually they're not continuing on with us in the spring. So, but they're fabulous, fabulous people. We just don't have them anymore. So hopefully that helps at least with a little bit of what's going on, what's happening. And I will also refresh the fact that when I was over on the 701 section, there are these exam blanks and keys for the spring 24 semester. These are really handy because some of the questions I often get are things like, what format do you use? What do some of the questions words look like? And this can be really helpful. One of the things though that I do want you to keep in mind, I'm just gonna look at one of the blanks and not even the entire thing, but just this front page. So this has the instructor list. This instructor list is not just your instructor list. This is also the list of authors of the exam. So last spring, we had Dr. Bacone, me, Dr. Diekman, and Dr. Wong. Those were the 4 instructors teaching the course. Those were also the 4 instructors writing the exam. Dr. Wong is off teaching physical measurements this spring. We miss him. I miss him already. And so he is not one of the authors of the exam this spring. So he has a certain writing style that will be missing. And as a result, there will be more questions written by Dr. Diekman, myself, and Dr. Bacone because Dr. Wong is teaching a different course this spring. So just to keep in mind when it comes to looking at previous exam, which is that you do have different authors, and that can play a role in how the question is phrased and exactly what we're looking for. So just something to keep in mind. Okay. So I am going to ask for questions from the chat. I do want to give you guys one more caveat, which I am so incredibly sorry for. I brought my tablet. I figured out right before this that apparently the pen slipped out of it, and it's either lost or, gosh, I really hope it's on my desk at work. So we are going to do a combination of me typing, which I do type pretty fast, as well as some of my handwriting with the trackpad. You have my deepest, sincerest apologies for that. That was definitely not my original plan. But that is what we are going to go with because I did not realize that quite early enough. I did come prepared with a set of questions. But in the meantime, let's go ahead and see what questions we have from the chat.
As of right now, I don't see any.
Okay, that's okay.
All right.
I will just continue on and see what I got. But I'll leave that there, so I've got it. Okay, so I did pull my class on Friday and asked them what questions that they had. So these are kind of in order. One of these says, I just wanted to review what will be on the test, whether it's logic or solving problems. I want to see the questions on the test and be like, oh, I've seen this and done this before. So this is part of the reason why I do recommend looking at the previous exam for things like wording. One of perhaps I think to me, it's one of the weirdest quote unquote things that we do that if you haven't seen it before, it can be a little bit strange, is when we do units, they actually will look like this. Which to say that your textbook and a lot of other sources will have a different way of showing this same idea. Here goes the trackpad. Um, some places would prefer to do like 1 over molarity or 1 over second, or it would just even be like a slash. I think I actually saw this in your textbook or in Alex, like a slash M for 1 over. Because of the way that the font size is, we will actually use superscripts and use that to the -1 power for the display instead. So even just in visualizing some of those units, taking a look at the previous exams is really helpful. One of the other things, though, to be aware of is that we purposely will ask questions that you have not ever seen before. That is absolutely done on purpose because y'all should be able to apply the information. I do understand you would really like it if we only asked you questions you had been directly asked before, and you'll certainly see some of those. It's not to say that there will be all of them will be a surprise, but just keep in mind that we continually are looking for new and creative different ways to display information as you guys are doing that. What's the best way of studying go over material if under a hypothetical scenario, you knew literally nothing about the chapter a day before the exam? So one of the weird things I'm going to tell you is that if you had no idea what was going on in class at all, to be honest, I would work on 14 over 13 because chapter 14 is going to be a bit more based on this lovely little box of equations. And so since chapter 14 is kinetics and it's going to deal with concentrations over time and how to apply those, as far as how far you could get through chapter 14 material with this equation list and like 3 hours of studying, you can I personally, if it was me as a student, I could get farther with less studying in chapter 14 than in chapter 13 because of the fact that the questions are phrased a little bit more similarly because they're concentrations in time for them a lot of the part. Chapter 13 has a lot more equations and different units to deal with. So those questions sometimes have a larger onus, a larger, what's the phrase for like, you have to put in effort for it on figuring out what you need. So chapter 13 questions usually are a little bit more involved in just determining what do you actually need out of all of this. Because there's a lot of stuff that you might use for a chapter 13 question. So many questions will be purely conceptual, which is that no numeric answer is required. I don't actually know. This is a wonderful question. I have to go with I don't know on this one. Whether I go with IDK, I don't know. This is in part because I did take a look at the questions, but we will not keep all of them. So we start with something like 32 or 33 questions, and we pare them down from there. We're aiming for somewhere between 28 to 30 multiple choice and 2 short answer. So we usually start with too many and pare down. So that's just something to keep in mind. So you don't honestly know how many are purely conceptual. More review on the math. This is one where Alex can be helpful. The other thing that can be helpful are workshops. So you think about reviewing on the math, I would definitely recommend the workshops that the various instructors give y'all on Fridays. Alex mentioned, and SI sessions can also be helpful on dealing with the math, and end of chapter problems. So all of those things can help with reviewing on the math. I will also say that one of the things to keep in mind is part of the challenge for this exam is doing the math under a time constraint. So keep in mind that for all of our exams, you have 80 minutes. If you take a look at how many questions we ask, which again, there's a range in there, it's 2 to 3 minutes per question, which is not a lot of time. So having that confidence in what you're doing and moving forward is really helpful. Let's see. Honestly, studying for this exam, this is going to be, I would say don't ignore the concepts. And especially when it comes to, I would actually tell you guys to know the names of the colligative properties, and I'll tell you why. Let me tell you why about this. It's one of the things that happens. So here are the names. So vapor pressure lowering, boiling point elevation, freezing point depression. The last one is just osmotic pressure. Osmotic pressure. So, okay, maybe not os. Can I spell today? Nope. There we go. Osmotic pressure. So granted, the osmotic pressure, not as much. But one of the things to me that is helpful is when I want to talk about, so what happens in a solution, after you add a solute. So if here is my lovely, lovely solution, and now we're thinking about going ahead and adding something to this, what's going to happen as I now have particles in here? Well, if I know the names, just the names of my colligative properties, then I can actually know that I expect my vapor pressure to go down. That's what's going to happen to my vapor pressure. My boiling point is going to go up. That's what the elevation means. My freezing point is going to go down. That's that word depression is going to happen in there. The osmotic pressure is the only one that doesn't particularly help. And honestly, that is in part because cellulose, it does go up. The pressure does increase as your amount of solute increases. That's the only one that's not included. All the others of these have a word in there in the English language to try to tell you what happens to the solution as you add more solute. So some of those things can help. I do understand that there are plenty of times where the terminology is not helpful. Colligative properties is a time where it does help. How to feel confident about test prep. Oh, my friends. I got all kinds of advice about confidence. I know that this is kind of cheating, but also general shout out, honestly, to online resources from the Counseling Center. If y'all have not, just search for in the UTD for the Counseling Center. They actually have a ton of resources, and they're all online. You can just click on things. Granted, I am all for if you want to talk to somebody, talking to somebody, and the fact that as students that is free is great. But there's a little tab that says resources and self-help. And the first thing says overview, and there are all kinds of articles about all kinds of things. And there's academic support, and there's self-care and stress management and all kinds of stuff in there. So granted, definitely all for talking to an actual human being, but there's also just links to click on. Because I definitely understand confidence. So exam anxiety is a very real thing. Everyone's got different tips and tricks for it. I will also tell you, I know this doesn't help a lot, that every person is different. I'll give you my favorite example. Apologies if you've already heard this one from me. So some of my friends, so this is me in college, some of my friends before an exam were passing out mint gum. The idea was that the mint flavor was supposed to either help your, I think it was supposed to help your memory or to help you like stay more alert with like the mint flavor. And the gum, chewing something was supposed to help like if you got distracted during exams easily. Chewing the gum was supposed to help your brain kind of like have something else to focus on, so that you didn't get distracted by like the rustling of papers or other things like that. I think that was the theory. Somebody told me right before the exam that this would help me out, and they're offering me free gum. Took it. I had braces, not at this time, but in general, and my like back molars don't match. I hate chewing gum. I hate it. Uh, so there I am in an exam, and about 5 minutes in, I am just annoyed out of my mind because I have gum in my mouth. So chewing mint gum is a terrible plan for me. It annoys me. It distracts me a lot. I do not like it. But there were some of my friends that came out of that exam and they were like, "Oh man, the gum was amazing." And they like always had mint gum on them for exams ever after. I am not that person. So everybody's different when it comes to that. So definitely kind of taking some time to think about where you fall on that one will be great. Um, the stuff we need to remember in order to do well, like maybe the stuff that we learned in Gen Chem 1. Um, so this is something that I've been trying to call out as we've gone along in class. I'm going to flip actually to your textbook for just a minute and try to show you guys something that I'm hoping will be helpful. So on the very beginning of the chapter, so what I just did is I flipped to the chapter 13. This is the introduction. So if this was a physical textbook, this would be the first page of chapter 13. It says physical properties of solutions. And down at the bottom, it says before you begin, review these skills. And it has intermolecular forces, and it also has solution stoichiometry. So the chapters themselves will actually try to set you up for success and help you review and remember things. So that will definitely be helpful. That being said, especially chapter 13 relies on all kinds of different things from previous chapters. So I will do my best to call it out as we go along. But I've got to fess up that chapter 13 just has a lot of stuff. For example, as your textbook points out, intermolecular forces is useful, and it is useful because we can ask a question that is something like, which of the following dissolves best in water? And I think actually, if I cheat for a minute and flip back to a question, there we go. So this just says, which of the following dissolves best in water, and gives you 5 different options. And the main trick to this question is intermolecular forces. I understand that it's asking you about dissolving, which is about solutions, which is what this chapter is about. But really, this is all about matching intermolecular forces. That's what this question asks. Is what intermolecular forces does water have, and which one of these 5 things has the same stuff? Because the top 3 things, carbon dioxide, sodium chloride, and methanol, all dissolve in water. Actually, so does the dimethyl ether. That also dissolves in water to at least some amount. Cyclohexane, not so hot. So most of these things can dissolve in water. The question is, what dissolves in water best? Which one does it the best? And we're actually asking you to compare intermolecular forces. That's what that one's for. That being said, we also covered things like enthalpy. in chapter 13, which enthalpy was a chapter 10 topic. And the other thing that is hanging out in my list of questions has to do with identifying what things will separate in solution, what things will give you more than one piece, what things are electrolytes. So I definitely respect this particular question, but it is really difficult to answer just because it depends on the topic. So to go ahead and let me address this one, because I showed you guys a question. So let's go ahead and talk about this. So one of the things to think about, so carbon dioxide basically is, they didn't draw in lone pairs, but it basically looks like that. It is what we would refer to as being non-polar. It is also a gas though, which is why it does dissolve in water. You can force it into there with increasing pressure. Sodium chloride, that is going to be a salt. More specifically, I can come over to a periodic table. No. I will come back over to a periodic table, but apparently I'll use this one that's already here. And what you should be able to see is I do in fact have sodium here on the left, and a chloride ion that is here on the right. This notion that I have something from this light green section that is a metal, and something from the far right-hand side in this blue section that is a non-metal means that this is an ionic compound. So without having to do any other work than taking a look at the periodic table, I should know that my sodium is going to give me an ion in solution. And so is my chlorine, will actually be the chloride ion with that -1 charge. This idea is recapped back from chapter 5, dealing with ionic compounds. But that is where that comes from, looking at where those two elements are on the periodic table. Methanol, not from the name here, but from the fact that they gave us this OH group right here. So that does mean that I'm going to have a couple of different features. So because I am in fact going to have a carbon with my hydrogens hanging out, this is sadder than I thought it was going to be. Oh, my pencil. You better bet that I'm going to order an extra Wacom tablet pencil, and then I will not have this problem ever again. But essentially what I am going to have here is, oops, my lone pairs. So this particular molecule of methanol is in fact going to have hydrogen bonding. And it is also going to have, it will also be polar, which means it has dipole-dipole interactions. Being a polar molecule automatically means that it has dipole-dipole interactions. And all of the molecules on here, no matter what, can be said to have London dispersion forces. So this is one of those times where we're not relying on the name, we're actually relying on our knowledge of what that looks like, and the fact that they gave you that OH there is supposed to help you identify what intermolecular forces that it has. That there is in fact a hydrogen bonded to that oxygen, which means that you could have another molecule interact with it. For example, like a molecule of water. So if I had my ever so very lovely water molecule, we're going to draw this kind of upside down. Here's my oxygen. And here are the hydrogens off of my water, not drawn to scale. I should expect to have a interaction in between the hydrogen of my methanol molecule and the lone pairs of my water molecule, because my water molecule also has hydrogen bonding, also dipole-dipole interactions. It also has London dispersion forces. So that one's all about intermolecular forces in there. The cyclohexane, you don't have to draw that one at all. It's nothing but carbons and hydrogens. Being nothing but carbons and hydrogens automatically means that this thing is non-polar. It's all carbons and hydrogens. The dimethyl ether's probably the only one on here that is, the dimethyl ether is the one that's trying to trick you. I was gonna say, what's the best way to describe this? It's kind of the one that's trying to trick you in there. We'll draw that one in red because it does have that oxygen in there, but this is what we refer to as a structural formula, which means that that oxygen is actually supposed to be connected to the carbons. So while we do in fact have oxygens and hydrogens in the same molecule, those hydrogens are actually connected to the carbon, which means that they're not connected to something that is electronegative enough to allow the hydrogen to form hydrogen bonds. For some people, that last sentence that I said did not make a whole lot of sense. For others, it kind of did. For some, it made perfect sense. That's a good reflection of trying to go back and refresh on some of the previous chapters. So, but the important part is in order for something to have a hydrogen bond, it still is in between a molecule. So intermolecular forces is always about being in between molecules. But in order to have hydrogen bonding, you have to have hydrogen connected to either a nitrogen, an oxygen, or a fluorine in order to actually have a hydrogen bond for the intermolecular force, because we are relying on having atoms that have so much electronegativity, they are going to pull most of the electron density away from that adorable little hydrogen, which is going to make my hydrogen a little extra positive. So if I didn't already say it, the answer to this question, dissolves best in water, is actually C, methanol, because we're looking for the things that has the exact same intermolecular forces. Okay, how are we doing with the chat? Any questions from the chat so far?
Yes, we have a couple.
Great.
Can you do practice questions with aqueous percentage solutions converted to moles or grams? Also, I can go slower because you don't have your pen. If that works
So
for you.
aqueous percents to moles or grams, okay?
Okay. All right. Could you go over the relationship between between vapor pressure, temperature, and the pressure of gas?
Okay.
How do we know when a math question is asking for Van Hoff factor?
Okay.
And could you go over boiling point elevation and freezing point depression? And that is all I see for now.
So let's do a math question needing the Van Hoff factor. 'Cause this is the one I think I might be a little bit different from some of my colleagues. So first of all, when we talk about the Van Hoff, or we talk about equations with it, one of the things that you might notice is that there are a set of equations hanging out in here, and some of them have this lovely little I. And that I is the Van Hoff factor. But you might also notice that there's a set of equations right above it that do not include the Van Hoff factor, which is fine. Personally, I just usually teach my class the version that includes the Van Hoff factor, so that it's always there, so that we don't have to ask which equation we're using. We just always think about the Van Hoff factor no matter what. Which means what we need to be able to do is figure out when the Van Hoff factor is 1, because that is the thing that often happens. So the Van Hoff factor, what it is supposed to do. Let me make that bigger. So the Van Hoff factor is supposed to basically describe how many pieces something breaks into. What I mean by that is, When I have something like sodium chloride, so here is my beaker, and we're going to put in here sodium chloride. When I put in sodium chloride, we looked at it earlier as being an ionic compound. That means I get a sodium ion and I get a chloride ion, and we are just going to say that this is in water. It's supposed to be water. We'll just roll with that. So essentially, because I have something that looks like it's all one thing, but because for colligative properties, the number of pieces matters. How many things I have in solution matters. That means that if I talk about the molality of the sodium chloride, that's actually going to give me the wrong answer, because I need to keep in mind that every time the sodium chloride goes into solution, I actually get a sodium ion and I get a chloride ion, which means here I would have a Van Hoff factor of 2 or an I of 2. So that way we just consider it upfront every time. So then the question is, of course, well, how do you know when you don't need it? Or how do you know when it's 1? Because there are certainly things that when you put them into water, it's just 1. One of those things, for example, I'm going to blow this up in just a minute. C6, H12, O6. Oh, come on now. So this is another particular compound. This is glucose, for those of you that are curious. C6H12O6. Also, if it seems like it's familiar, that is why it is in fact sugar. So you might have heard about it from photosynthesis. This thing, if this goes into water, then we just have this. It's just a sugar and it just hangs out and it doesn't change. And there's nothing interesting that happens to it. So this would then give us that I value of 1. So some of the ways that we're going to know that we have an I of 1 versus an I of 2. So if I have an I of 1, we might actually go ahead and tell you that it is, I'm going to make this bigger in just a minute, a non-dissociating solute. What we mean by that is that it doesn't separate. So sometimes we will just flat out tell you that it is a non-dissociating solute. Means that is another phrase for an I of 1, a non-dissociating solute. You don't have to worry about how many pieces it breaks into. It has an I of 1. Another phrase that means the same thing is a non-electrolyte. So that is a phrase that is back from Gen Chem 1, when we were talking about what things essentially, if you put them into solution and then you try to, what things will give you ions in solution and what things will not. Non-electrolytes don't give you any ions in solution. They don't break apart into any pieces. So those two phrases are phrases we might very well use in questions to tell you. Another thing to keep in mind and look for is especially lots of carbon, because a lot of our organic compounds will oftentimes be non-electrolytes or non-dissociating solutes. About the only thing to keep in mind is we could do something where we ask you to solve for the Van Hoff factor itself. So we could definitely do something where, let's draw carbonic acid real quick, H2CO3. This is a weak acid. The ways that you would know that this is a weak acid are as follows. So you might know that this is a weak acid because it has a hydrogen in front, which would just tell you that it's an acid. You might not know that it's weak from that. And the other thing is that we would ask to solve for the Van Hoff factor. So there are times where the Van Hoff factor, if we ask you to solve for it, it is likely going to be not a whole number, not just 1, or 2, but somewhere in between, in which case we'll ask you to solve for it. So if we ask you to solve for the Van Hoff factor, then you need to go ahead and assume that it is something we're solving for, that it's not just 1. But this would probably be the only time you guys would actually see something with carbon in it, where it wasn't a non-electrolyte, but then we would be asking you a question about it that you would need to solve. So hopefully that helps with some ideas of how you would know. So then keep in mind over here, when you do have to worry about the Van Hoff factor and you do have to consider what's going on, that this is the part where what you're going to really want is the periodic table, because that's going to help you identify that idea of a metal plus a non-metal, so that you can be prepared to identify ionic compounds. So that way you're like, this is an ionic compound, that's a metal, that's a non-metal. That means that I need to think about the Van Hoff factor. I need to go ahead and incorporate that I into the equation. It's not just 1, something else is going on here. The other thing that could help with that would be polyatomic ions. So thinking about another thing that would be a good thing to know for this upcoming exam are your polyatomic ions. That exact list is hanging out in chapter 5. Do I still have, yes, there's a textbook. Get rid of that, there you go. So back to our textbook, chapter 5, ionic and covalent compounds. Somewhere in here, polyatomic ions. And there is a whole list in your textbook. So this is the list that we would use. So you can have your opinions on how long the table is, how short the table is, any of that jazz. The table 5.10 is a list of polyatomic ions that we would use. The main thing for those of you looking at this for the first time is your textbook does the polyatomic ions in alphabetical order. Personally, I think that that's silly because there are some of these that are actually related to each other, but are not alphabetical, or not in alphabetical order. My favorite example is if you find all the ones that have chlorine in them. There's 4 of them, but only 2 of them are right next to each other. So just be aware that if you're looking back at polyatomic ions, that your textbook does in fact still put those in alphabetical order. So that would be another thing that might be potentially helpful as you guys are looking at those. Okay. So as far as answering the question, when do we need to incorporate the Van Hoff factor? One, that really goes in 3 places. For a freezing point calculation question, a boiling point calculation question, or an osmotic pressure question. So there's really only 3 places for a calculation question where you would be given information and need to worry about the Van Hoff factor, in freezing point, boiling point, and osmotic pressure, as those are the 3 equations that have that I in them. The Van Hoff factor does affect vapor pressure. So you can have a conceptual question that does ask about the Van Hoff factor that includes vapor pressure lowering. However, we would not do a calculation question with the Van Hoff factor and vapor pressure lowering, at least not on the exam. You might see that in an end of chapter question. The math is just a bit messier. So it's not that it makes a lovely conceptual question. It makes a lovely conceptual question. So then of course the question is, what do I mean by that? So looking at the 2 things I have right now, right? I have a glucose solution with an I of 1. I have a sodium chloride solution with an I of 2. If I had gone ahead and just said that this is we'll do osmotic pressure. No, it doesn't. we'll just call this a 1 molar solution of glucose, and we will also call this a 1 molar solution of sodium chloride. And then the question is things like which has the lower vapor pressure? So here are my two solutions, and the question, which I of course need new space for it, which solution has the lower vapor pressure? So this is one of the ways that we can incorporate the Van Hoff factor, but not actually into vapor pressure lowering, but not actually have you do the math for it. So given two solutions, a 1 molar solution of glucose and a 1 molar solution of sodium chloride, which solution has the lower vapor pressure? So one of the inclinations is to say, but they're the same because they're the same molarity, they're the same concentration. But the point here is that because my sodium chloride solution has that I of 2, because I actually get I get double the number of solutes, double the number of particles per molar solution of, or per mole of sodium chloride, I actually have more stuff in the sodium chloride solution. So even though they're both 1 molar, and that's the same number of moles per liter, my sodium chloride is actually breaking into pieces. My glucose solution doesn't do that. So when I'm looking for the lower vapor pressure, I'm looking for the one that has the higher I value in this case. So the lower vapor pressure is going to be my sodium chloride solution because I have more pieces. My sodium chloride solution gives me both sodium ions and chloride ions. I have more solutes in there. I have more things in there. I have more particles in there. More particles is going to give me the lower vapor pressure, even though the concentration of the whole thing is the same. That's where my value of I is going to come into play and tell me that I have a lower vapor pressure solution with my sodium chloride solution. Okay, I have answered one question. One of these is about some of these other so yeah, I'm gonna say one more. So the relationship between vapor pressure, temperature, and the pressure of the gas. So speaking of vapor pressure, so first of all, a definition of what vapor pressure is. If this is my container, and here is my liquid line, and then I put a lid on my container. One of the things that has to happen is my lovely liquid, there will be particles of this liquid that just go into the vapor phase. So first of all, when we talk about vapor pressure in general, we're talking about how much gas does the liquid give off. We're kind of asking about evaporation. So we're basically asking how much vapor, how much gas does the liquid give off when we're talking about vapor pressure. So just vapor pressure in general, not talking about adding a solute of any sort quite yet. Just how much gas does the liquid give off? So when you think about this, so things like perfumes or colognes have a really high vapor pressure. You can smell those really easily. Things like water actually usually has a relatively low vapor pressure. It's there, it exists, but it's actually lower because the intermolecular forces actually keep more of those particles together. So things that have a lot of sense usually have a lower vapor, have a higher vapor pressure because you can get more components, more things into the gas phase. So the measure of vapor pressure is the measure of this gas. So you talk about the relationship between vapor pressure and the gas. Vapor pressure basically is a measurement of how much of the gas do you get. So if this, for example, was saying that my vapor pressure is equal to, we'll just do something like 100 torr, to use an interesting to use an interesting pressure unit. But we'll say that that's at 50 degrees Celsius. So if my vapor pressure is 100 torr at 50 degrees Celsius, that tells me how much the pressure is in my box. I would basically expect that in here that I have 100 torr just from the liquid. So this is basically assuming that I started with a vacuum. But it's 100 torr from the liquid alone. From liquid alone. So one of the interesting things about vapor pressure is it's a property of the liquid. So whenever you talk about vapor pressure, you are in fact describing something about the liquid, but you're actually describing how much gas the liquid gives off, which is why vapor pressure is kind of a strange thing, because you say the word vapor a lot, you say the word pressure a lot, and those are things we associate with gases, and they are, but this is all talking about the gas that comes from the liquid. How much gas does the liquid give off when it just sits there? The other question incorporated in this was, what about temperature? So this is something that you may not have noticed, but this does in fact happen. We'll just call it 150 torr at 60 degrees Celsius. But sometimes if you see a fair number of questions, you'll actually see this one as you go along, which is that will then give you the exact same liquid, but then suddenly we'll be like, and now we're at a different temperature, which means we're at a different vapor pressure. So you might have actually realized this, except that in the real world, things also get complicated, but typically, so vapor pressure increases as temperature increases, period, no matter what. So the vapor pressure of any liquid does go up as temperature goes up. So if your temperature is going up, then your vapor pressure also goes up. So the way that I don't know if you've ever noticed this before, but if you do ever try to like watch puddles evaporate, they sometimes will evaporate faster in the summertime than in the wintertime because your vapor pressure is actually higher, and so being able to get more vapor off of that liquid in a shorter period of time does happen with hotter temperatures. The reason why I was like, sometimes this happens is because in the real world, you also have to deal with this notion of humidity, which is a totally different thing. But in general, as temperature goes up, vapor pressure does go up. And really for us, there's two reasons why that's useful. One of those is because that way questions are not trying to lie to you. We have a tendency to pick water a lot when we're dealing with solutions, and that's because you're relatively familiar with water. So if you see a variety of different vapor pressures for pure water, a lot of times we'll include temperatures in the problem just to try to be honest, so that you don't think that the vapor pressure of water is this transient thing and that we just made it all up. The truth is that the vapor pressure of all liquids change with temperature. So you'll oftentimes see temperatures given in vapor pressure questions, just so you don't think that we're lying to you. The other reason why this is potentially helpful is if you want to talk about boiling. So the definition of boiling is when the vapor pressure is equal to the atmospheric pressure. So this has to do with the idea that to get something to boil, you do have to increase the temperature. So having a warmer temperature eventually will get things to boil. But if you'll notice, this whole notion of giving gases off the liquid, well, if you wanted all of the gases you wanted none of the liquid left, you just want all of it to be a gas, then basically you need to make that vapor pressure go up and up and up and up until all of the liquid should just be in the vapor phase. So increasing your vapor pressure to the point that you have nothing but gas, that is what boiling is. So boiling point and vapor pressure are actually connected because they actually are connected by definition. As you increase temperature, you increase the vapor pressure. And if you increase the temperature enough, you get to the point where the vapor pressure of the liquid is the same as the atmospheric pressure, in which case everything becomes a vapor, everything becomes a gas, all connected together. So hopefully that helps with some of those connections. Again, so you will usually see temperatures given in vapor pressure problems. This a lot of times is just because we're trying to be honest with y'all with where things come from. We're getting close to 4 o'clock. Any other questions from the chat right now?
Yes, there is a couple. Could you go over some Raoult's law example problems?
What else?
And then just asking, this will be uploaded on e-learning.
Yeah.
And that's all.
Okay, cool. Yeah, so to go back real quick to that 701 section. So 701 section on the course homepage, there is a folder that just says midterm exam reviews. And there is a folder that says exam 1 reviews. And this will have the recording link posted once I have it and I have seen it, because there is always a delay between the living learning community giving me the link and me posting it. So those are things. But yes, that does exist. Oh, what do I do next? So we talked about so we've been talking about vapor pressure. Let's go ahead and talk a little bit about that boiling point elevation, since that last conversation about how vapor pressure and boiling point are connected go fairly well together. So we'll just start with a relatively straightforward question. Do I have one already? Oh, let's do this one. So I did also poll my class, and lucky for me, my class, somebody actually asked me for one of my workshop questions, and this one has a boiling point question, but it also has a percent in it. And somebody else also wanted to talk about aqueous percents. So we'll just do a little bit of all of it in this question. So it says, what's the boiling point of a 20% by mole? How weird is that? So we still do a different percentage of fructose in ethanol. And then it has information for ethanol, giving you the boiling point and giving you this factor, the KB as well. So flipping over quickly to my potentially useful information page, I'm going to grab a couple of things that all have to deal with boiling point. So all of these little B's. So that way we can take a look at those together. And I'm also just going to go ahead and grab this table because I do understand that this particular problem went ahead and gave it in the problem, but I do also want to demonstrate where the information would be located were we on the exam. So first off, so this does say of fructose in ethanol. So this is in fact not using water. So it says it goes fructose and it gives ethanol here. So my ethanol then is hanging out in this table. So I do in fact have a whole line here for ethanol. So I've got a whole line. It's in the very center of the table. The question itself asked for boiling point. So therefore, I want boiling point, and I also want KB, the B also for boiling. So what you might notice here is that the information in the problem itself was exactly the same because it was pulled off of this table. But again, on the exam, we would actually not give you guys this information in the problem. We'd expect y'all to flip to the back page and take a look at this table to grab the boiling point and to grab the KB information. Then from here, we have some decisions to make. This is fructose. So the question is, do we need that I, or what's going on with I? And what I do want to point out is this, even though it's fructose instead of glucose, this is all a bunch of carbons. This is in fact a sugar. So this is going to have an I of 1. So we can either use this top equation that doesn't have the I in it, or we could go ahead and use this equation knowing that I here is just the number 1. So when we multiply it out, it'll essentially go away. So basically what I have so far is I need the boiling point. I have a lot of information about ethanol, and for an equation where I'm going to be solving for the change in boiling point, I have a KB value, my 1.22. I have the value of I. We decided that because it's all a bunch of carbons as an I of 1. So now all I need is the molality. So this is now where what I need to be able to do is go ahead and solve for molality based on what I already have. So this is really going to be a lovely unit conversion question. So I have 20% by mole. What that means is I have essentially, and there's different assumptions you can make, but this is my personal favorite assumption, is that I have 20 moles of fructose out of 100 moles total. So anytime you have a percentage, my personal favorite is to just assume that you have whatever the percentage is out of 100. The beautiful thing is because we are dealing with concentrations, you can make a lot of different assumptions and it doesn't matter. If 20 moles and 100 is just too big, you could also decide that this is 0.2 moles out of 1 total. As long as the ratio is intact, it doesn't matter which one you choose. So this is one of the perhaps the strangest things about doing unit conversions is you get to pick what that total number is. If you really wanted it to be 50, you could do 10 moles out of 50 because the 20% is still intact. The ratio is still intact. You want to do 1 in 5, that will also work. The ratio is still intact. And this really goes back to the idea that when we're dealing with concentrations, I'll bring back my lovely Dr. Pepper can. It doesn't matter for the purposes of this question if I'm trying to describe the amount of sugar, since this is fructose, the amount of fructose that's in this particular can that I'm holding in my hand, or if I want to pretend that I work at the Dr. Pepper factory and I'm actually talking about a like giant vat of Dr. Pepper and that's going to go into a bunch of cans, but I'm instead staring at like a swimming pool full of Dr. Pepper. It doesn't matter. The concentration, how much sugar there is per like sip, how much sugar there is per unit to enjoy, that ratio is going to be the same whether I'm talking about a can or about a swimming pool or an ocean. Doesn't matter. So this is what I'm starting with. I start with 20 moles of fructose in 100 moles total. This is again, that's moles. And where I'm going is I need to go to molality. I'm actually going to go back to the potentially useful information page because, believe it or not, we actually gave y'all the definition of molality. This is part of the reason why I would encourage y'all to work with this, because you have a surprisingly large amount of information on there. So this is where I'm headed. I have moles of, I have 20 moles of fructose and 100 moles total. I need the moles of solute divided by the kilograms of solvent to solve the problem. Well, lovely thing. This 20 moles of fructose is my moles of solute. That's the same. So I haven't done any math yet, but I have so far solved half of this fraction. 20 moles of my fructose. So there's a start. Then I gotta deal with this solvent problem and the fact that I need kilograms, but I have 100 moles total. So what I am going to be able to do for that is when it says total, that means that I in fact have, that is my solution, which means that's going to be my solute and my solvent. So when it says that that is a total, that actually means that I have my solute and my solvent together. So the lovely thing about this is that we already said that my total or my solution is 100. And I already said that my solute is 20. The problem needs me to solve for a solvent. So I can just make that X. And I can go ahead then and solve. So here, now all I'm going to do is subtract 100 minus 20. So now I have 80 is equal to X, or 80 moles is my solvent. So I now know I have 80 moles of whatever my solvent is. What was my solvent again? We've been talking about a lot of different things. Ooh, my solvent's ethanol. One of the trickiest things in here is the fact that this is not water. We ask about water like 95% of the time, sometimes more, but this is actually ethanol. So when I say, hey, I have 80 moles of solvent, that's great. And I can, in fact, go ahead and take my 80 moles and go ahead and get to kilograms. But we've got to keep in mind that this is ethanol. That's what the problem said. That's what we're using. So I've got 46.07. So again, I know everybody is sorry that I left my Wacom tablet pin in my office. You will likely see me do this exam review from my office next time, and that'll help me a little bit. I can go ahead and end the problem here, but since I also know I need this to be in kilograms, I'm going to go ahead and do one more thing, which is to say that there are 1,000 grams in 1 kilogram. I've done all of this backwards. Great. Oh. Erase, erase, erase. So the mole goes on the bottom. I need my moles to cancel out. I was like, wait, something looks weird. Moles go on the bottom. So again, my 46.07 grams goes on the top. Again, my apologies for the handwriting. And then there are 1,000 grams in 1 kilogram. One thing to note as I go ahead and do this calculation, in that potentially useful information page and periodic table, those are all that you get. There's no additional information aside from that potentially useful information. So we do not give y'all any metric conversions. So all the metric conversions are things that you do need to have in your brain. So there is my number in kilograms, 3.6856. So again, now trying to do my molality here. I now have my amount of my solvent. So I had my 20 moles of solute in now kilograms of solvent. So for a molality, Now I can go ahead and say that this is 0.4, we'll go ahead and go with 27 mol. That then value, I can then, so now that I have my molality of my solution, now I can come over to look at my equation. So I need all of these lovely pieces. So in order to solve for my change in temperature, I'm going to use my value of Kb. My value of Kb is going to come from the table that we've talked about, that 1.22. So 1.22 is the value of Kb for ethanol. Again, it's highlighted here, but again, we are not using water because the problem is not using water. So 1.22 for Kb. And then my I value is 1. And then my molality is that 5.427. So that is then the calculation I'm going to use to calculate my change in temperature. I am going to hold on to a few extra decimal places because I still have it in my calculator. So that gives me a change in my boiling point of 6.62. That is in degrees Celsius. So I was a little bit lazy, but if you'll take a look back at this table, you can actually see that I have units here. So my KB value in what information y'all are given does actually give you the fact that that's in degrees Celsius per molal. So anytime you're like, am I in Celsius? Am I in Kelvin? What am I doing? You can actually flip back and take a look at that back page and it'll actually tell you which units you're supposed to be in. They're actually given there. So I have the change in my boiling point. To get my boiling point, since this is boiling point elevation, I am in fact going to add them together. But again, this is not water. This is not water. So I'm going to go back to my table. The boiling point of ethanol is 78.4 degrees Celsius. So I'm going to take that 78.4, and that is what I need to use. Not gonna lie, this was the part that I was the most concerned that I was gonna mess up because we use water a lot. So making sure that we are addressing the correct solvent, which in this case is ethanol, super useful. So 78.4, which is the boiling point of ethanol. My new boiling point of the solution is about 85. Technically 85.02. I don't know that I need that many digits. Degrees Celsius. So one of the things in working with boiling point elevation problems or in freezing point depression problems is don't be afraid to go back and utilize those equations that we've posted for you that you have on the exam, because it sometimes is really easy to skip steps. So for example, depending on who writes the exam questions, we have a tendency to ask for the final boiling point, which in this case is 85. But one of the answer choices that we usually give you guys as an option to select from on a multiple choice exam is the change, because there is this idea of like, but I did it. I did the hard part. I figured out if I needed to deal with I found the constant that I needed. And I got my molality and I have all of the things I need. And you solve for the change. And not always, but often one of those multiple choice answers is that value. Even though the answer that you actually need is after you've added it to the original boiling point. So just do keep that in mind that we have to find 5 different answer choices and only one of those answer choices can be the correct answer. So sometimes we are desperately looking for other numbers so that you have 5 answer choices to pick from. So even though the right answer is 85, you might very well see another number that you can easily come to with your calculator and the values given. So there's one example of boiling point. Then one of the other questions was dealing with freezing point. And let's go ahead. Where am I? Let's go. So we did a boiling point elevation question. I know I only did one, but there it is. So let's actually take a look at this exact same problem if it was a freezing point depression problem. And let's just look for a moment at where it's similar and where it's different. So we're not going to redo the molality piece. So if I instead wanted to solve for freezing point, if it didn't say boiling point, but it instead said freezing point, if we did freezing point instead of my 20% by mole solution of fructose still in ethanol, what would that look like? So going back to my equation sheet, now I'm going to look at all of the equations that involve the F. So I'm just going to look at all of the things now then that have the F involved. Some of these pieces are going to be the same. So grabbing my original question, I still have that fructose that I'm dealing with. So I'm still dealing with that I of 1. So still have fructose, still have an I of 1. We now, though, are, again, going to deal with freezing point instead. So now I need Kf. So I do have a different constant. This is still ethanol, so I'm still in my highlighted section, but now I have a freezing point of this 1.99 instead. So when I'm taking a look at that equation, some of it's the same, but I do in fact have a totally different constant. So that 1.99 is for my Kf. My I value is still 1 since it's the exact same solute, and my molality will actually be the same because it's the same concentration. So I'm not going to go through and do all of my mole percentage again. I'm just going to sneak in here and grab my molality. So that is that 5.427 value again. So we are going to trust that that molality is done correctly. So there's my molality. So here's my freezing point problem, where again, I do have a new value for Kf, but my I is the same, my molality is the same. So when I get my change in temperature, I will have a different value because of that molality change. So now I have a change of 10.8, like 10.7997. Should we go at 10.8? But now one of the other things you might notice is my freezing point question has a negative sign, has a subtraction sign in there. So what's going to happen is this is freezing point depression. My freezing point actually needs to be lower. So this is just my change in my freezing point. So I need to scroll back up and grab my actual freezing point, which is negative, kind of low, negative 117, negative 117.3 degrees Celsius. So negative 117.3 degrees Celsius. And then I'm going to subtract, right? This equation here tells me that my freezing point needs to go even lower. So I am in fact not going to add anything. I'm going to make sure that I am subtracting that so that my freezing point is a lower number. Because it is already a negative number, it is going to be even more negative number. Don't know if that was proper grammar, but we'll just roll with it. So my new freezing point is negative 128.1 degrees Celsius. So again, we're using ethanol, so we're still using something that's not water. And since I have a freezing point depression, my freezing point should go lower than what we started with. So my boiling point goes higher as the addition sign, my freezing point goes lower. And again, I can know those things from remembering that it's freezing point depression and boiling point elevation. I can, however, also flip to that potentially useful information and take a look at my equations and see that the equation calls for my new freezing point to have that subtraction sign in there. I'm going to make a lower freezing point than when I started. So whether you are a person that remembers the names of things relatively well and can then think about that freezing point depression that way, whether you're an equation person and you're like, we're going to think about this from the equation standpoint, and there's that subtraction sign in there, or if you are a conceptual person, I'm going to grab, oh, there's so many slides. So this is taking a look at the phase diagram of a liquid, and then this dashed line underneath here is taking a look at the solution. So trying to highlight it here in yellow. This line here is my solution. And what I want you to notice is that essentially it makes the liquid phase bigger. When you have a solution, you essentially have a liquid at a wider range of temperatures. Here's temperature here on the x-axis. So I have my original freezing point hanging out. That's always so many reds. So here's my original freezing point. And then here is my freezing point of the solution. So my freezing point gets even lower. I have a liquid at even lower temperatures. Here is my boiling point of the original solvent. Here with the X is the boiling point of the solution. I have a liquid at even higher temperatures. So you basically have a liquid at a wider range of temperatures. So the temperature range where your liquid is stable goes in both directions. That's one of the interesting things that we don't often talk about because it's more of a physics concept, which is that adding a solute to a solvent, adding solute into your liquids usually stabilizes the liquids. Your liquid typically is more stable. You have it around more than you do the other phases. So all of those things go into dealing with freezing point and boiling point. Okay. I'm pretty close to 4:30. Let's go ahead and see if there are additional questions in the chat.
Yes, there are a few. Can you please do a question with rate law, exponents, and K value? Could you go over how to look at the Raoult law graphs and how to label them and everything?
Okay.
Why did you plus the 78.4 and 6.62? And that is it for now.
Great. So we'll go ahead. You can see my misspelling as I'm typing too fast. So let's go ahead and take a look at the question that is addressing some of the math that I just did. Make that a lowercase k to make myself feel better. So the question is why did I add? Why did I add? So I'm going to assume that addition is asking because it was about the 78.4. So my 78.4 from the table, and I know I have to scroll around a whole lot. So in my section, I did it last Wednesday. I actually passed out a physical copy of the potentially useful information page. I say that because I like to try to emphasize that it is helpful to just have the potentially useful information page with you. Now, the other reason why I say I passed it out last Wednesday is because if y'all manage to like poll the students in my class, a number of them don't have it anymore because it's a physical piece of paper and it's now lost and gone forever. They don't remember that because it was not this morning. They weren't there because it was Wednesday, whatever. So I'm telling you that because there's a number of reasons why I pass it out in class, and also a number of reasons why I understand passing it out in class does not magically fix the problem. So potentially useful information page is available in the 701 section. I highly recommend that you, if you're working on a tablet or something, that you just keep it somewhere where you can see it. I'm in OneNote. I just made this thing that says useful info sheet so that I can click back to it whenever I need to. Super useful because it's this table that's in the middle of the potentially useful information page that I'm referring back to, of where I got the boiling point for the ethanol. So that 78.4 is the boiling point of the ethanol. I added to it because the first problem that I did asked for boiling point. So because the first problem that I did asked for boiling point, I added. That is why there is an equation that has this little T sub B equals T sub B naught plus the change in T sub B. This equation down here is because it's trying to tell you that the new boiling point, T sub B, is equal to the original boiling point of the solvent plus the change in the boiling point, which, to be fair, I should have gone over all of that. So this not symbol here is going to refer typically to your solvent because it's trying to point out that it's the original, it's the OG, the original thing. So that not symbol is usually the original, whatever you started with. So therefore its lack is typically going to be the solution in here. So I was in fact basically following the equation, but also since it's boiling point, you could also consider the fact that I added because it's boiling point elevation and I need that value to go up. I use 78.4 because that's the boiling point of the ethanol. The problem uses ethanol instead of water. So hopefully that helps with that particular question. So what are we gonna do first? Let's go ahead and do a rate log because we've not done anything out of chapter 14. So if I can do a little bit of chapter 14, let's do that. So we are going to do finding the rate law given a table of information. Which means I have to make up some information real quick. So, oh gosh, good. It's going to make a table for me. No problem. So I've got a concentration of A. We will also do a concentration of B. We will also do a concentration of C because based on class went this morning, I might need all of those. There we go. 0.1, 0.1, 0.1 to make my life easy. 4. And then we'll double A, but we will leave B alone and we will leave C alone. And if we double A, we're going to say that the rate doesn't change at all. And then we will still use 0.2A. We'll now go ahead and double, oops, I double 2 of those. And we'll leave C alone. And we'll say that when this happens, my rate goes from 4 to 64. And last but not least, if this stays at 0.2, and this goes back to 0.1, and this goes to 0.3. We will say that this goes to 12. So this, I really wish that the lines on this table were bigger. That'll help a little bit. So we're just getting a little bit of space in here. So my grand plan for this is to try to demonstrate how to deal with changing concentrations and rate laws. So this is the idea. We are going to assume that my reaction is in fact A plus B plus C. So I have 3 different reactants. We'll just say that this all comes together and goes to D. So that's my chemical reaction. And the goal is to come up with the rate law and a value of K. So find the rate law and find the rate law, find the value of the rate constant, and what is the overall reaction order. Lovely. So, sorry, I'm trying to make this bigger so you guys can actually see it. Oh, OneNote. Okay. So we're going to do 3 different things with this table of data. And we are, in fact, going to do them in this order. So, first of all, I can write a generic rate law. So my generic rate law will look something like this. The rate of my overall reaction is equal to my rate constant. That's just my lowercase k. And then I need to address every single piece. So here is, so I need to know how the change in a concentration affects the rate. It's going to affect it in some way, shape, or form, and we are going to mathematically represent how it affects the rate with these exponents. So the exponents that I have drawn are going to demonstrate how the rate changes. For us in General Chemistry 2, for Chem 1312, X, Y, and Z will either be 0, 1, 2, 3, or 4. They will be either 0 or a positive whole number. In the real world, things are more complicated, but this is the part where, for the purposes of this course, we're just trying to get you guys to look at the fact that it could be something more than just a straight linear relationship. That a linear relationship is not the only option. So I have a table of data. Now, since I did make this up off the top of my head, another thing to note is that these are all individual experiments. So this is experiment 1, where we have a certain set of concentrations. Experiment 2 with a different set of concentrations. Experiment 3 was run with a different set of concentrations, and experiment 4 was run with a different set of concentrations. And what we then looked at was what was the initial rate of the reaction when we had all those different concentrations. So every single line of data is a completely different experiment, completely different setup from scratch every time. One of the things to note is, in order to figure out how start at the beginning, we'll go with A, to figure out how A affects the rate of the reaction, I would really like a place where A changes, but nothing else does. So as I'm looking, this first one, everything is 0.1. That's lovely. And then in the second line, I have where both B and C are 0.1, but A is different. This is your ideal situation where only one thing is changing. This is great. So I'm going to use these. Now, there are a couple different ways to do this. For this one, I'm actually going to do it by eye, and we'll see how much it upsets you. Because one thing I want you to notice for this is B and C don't change. So neither B nor C should have an effect on the rate. So even though they are in fact part of the rate law, for the thing that I'm looking at right now, B and C basically don't matter because they're not changing. They're not going to have an effect on the rate because nothing happened to them. What did happen is A changed. So A doubled. A went from 0.1 to 0.2. But when I look at what happens to my rate, nothing happens to the rate. So I doubled the amount of A and absolutely nothing happened. That's interesting. Basically, what that means is A doesn't matter. A does not affect the rate. So even though I drew it down here in the rate law, it doesn't really belong in the rate law because it's not, because this is essentially an equation to describe what the rate of the reaction is. But you can change A all you want, and it's not going to change this. So that exponent there for X should just be 0. So if you plug things into your calculator, what you will actually find is if I look at A raised anything raised to the 0 power, so I could take 0.1 and raise it to the 0 power, I will actually just get the number 1. I could take any number. I can take the number 12 and raise it to the 0 power, and I just get the number 1. So this idea that when I look at the overall rate of the reaction, A doesn't affect it. Doubling A did not change anything. So that is one of the ways to solve the problem of what is changing, what's going on. We're comparing two things, and one of the options is just to look at what happened and come to a conclusion. I have to say that 0, an exponent of 0, is one of the easier ones to spot because of the way that this format sets up. And let's go ahead and take a look at what happens if we actually do the calculation and do some math with this. So in this case, I'm going to look at B now. So I would really like a place where B changes, but nothing else does. As I look in this table of data, I have places where B changes, but really I only have one spot where B is changing, which is in experiment 3. So there I actually have a 0.2. It's up to you whether you use 1 or 3 or 1 or 2, but honestly, this second experiment works just fine because even though A is 0.2, you can see here it's also 0.2. So even though A is not the top value and that 0.1, between 2 and 3, A does not change. Between 2 and 3, C does not change. It's exactly the same number. Between 2 and 3, B does change. And that's what we're looking for. We're looking for something where one of these is changing, but the other ones do not. So what I am then going to do is do this one mathematically out so you guys can see what that looks like. So what I'm going to do is I'm going to use my rate law that I have down here. And essentially, I'm going to make a ratio because as long as I incorporate true statements, I can use that. So what I'm going to do is take my rate law that I've already written out so you guys can see that is what I'm using. And what I'm going to do is I want to pick those two rates those two lines, 2 and 3. I'm going to put the larger one on top. So here's 64 and 4. So I'm going to put experiment 3 on the top. So absolutely everything that I do, I'm going to have experiment 3 on the top divided by experiment 2. So experiment 3, no, do not translate that. Experiment 3 by experiment 2. Go away, OneNote, thank you, by experiment 2. So experiment 3, the rate for experiment 3 is 64. The rate for experiment 2 is just 4, equals a value of K that I don't know yet from experiment 1 and from experiment 2 and experiment 3. My concentration of A from experiment 3 is 0.2 raised to the x power. For experiment 2, it's also 0.2. So that is A right there. Then B, experiment 3 is 0.2. We'll use a different color. We'll use red, 0.2. All raised to the power of y divided by 0.1 from experiment 2, all raised to the power of y. And then we'll also take C, which between experiment 2 and 3 is they're both 0.1. So C is 0.1 raised to the z power divided by 0.1, also raised to the z power. Now, I wrote all of that out ironically so I could get rid of almost all of it, because I don't know what K is, but I have K over K. Anything divided by itself is just 1. So I actually do know what A is since we already solved for that one. But if I wasn't solving for A first, I still have 0.2 to the x divided by 0.2 to the x. That also is just 1. This part and my rate will be different. So I can take 64 divided by 4 and I get 16. And then here I have 0.2 divided by 0.1. So that is 2 raised to the y power. Then I have 0.1 to the z divided by 0.1 to the z. That's also just 1. So what I now have is I have 16 is equal to 2 to the y power, because everything else canceled out. Everything else is just 1. Now, this is the part where I think Alex has y'all do logarithms. Logarithms are all well and good, but again, I promise you that y is a whole number. So all we're going to do is what I like to refer to as guess and check. So if y is equal to 1, then I have 2 to the 1 is just 2. That's wrong. That's not 16. I could have 2 squared. That would give me 4. That's also not it, because 4 is not equal to 16. I could have 2 to the 3rd. That's 8. 8 is also not 16. I could have 2 to the 4th. 2 to the 4th is 16. So that's supposed to be 2 to the 4th power, not the number 24. That's a little clearer. So personally, for me, I like guess and check, because 2 to the 4th power doesn't take me very long on the calculator. And while I went ahead and wrote out 2 to the 1 is equal to 2, with some practice or some remembering, you would probably be able to skip that one. But basically, you can just do guess and check on your calculator and find that y equals 16. The reason why I give this as an option is because for some people, y is equal to, nope, y is equal to 4. Y is equal to 4. Because for some people, guess and check with whole numbers is faster than learning logarithms. I don't know if that's you or not. Also, some people don't need to learn logarithms from scratch. Some people remember them from high school. I also don't know if that's you. So when I teach it, I actually just teach a guess and check, because that is one way to do this. So we've done just stare at it. Oh, look, nothing happened. That's 0. And we did what the heck happened. That went from 4 to 64. And so we actually went ahead and did some mathematics for that, to figure out that y is equal to 4. Our last one on here, then it's up to you how you would like to do this. But I will go ahead and show it off in both ways. So I'm going to go ahead and actually do it the mathematical way first. So the goal is to find a place where C changes, but nothing else does. So C is always 0.1, except for when it's 0.3. So I am definitely going to be using this experiment 4. I have to, because it's the only place where C changes. Then I would like a place where B is the same. B is the same experiment 1 and 2. So for B, it doesn't matter. But here is A, and so I'm just going to find the place where A is the same, which is experiment 2. There are different ways to do this. For example, because I know now what 2 of my exponents are, I could actually just plug in for the exponents because I have 2 of them already and use any line of data that I'd like. But I'm going to keep kind of showing off the same thing, so it really wouldn't matter if we started with C or if C was the last one that we did. So I'm going to use experiment 4 and 2. So those are the 2 that I'm going to use. I'm going to use experiment 4 and experiment 2 to solve for C. So same idea as what we did before. I have this lovely, lovely rate law that I am working with. And as I mentioned, we are going to do experiment 4 and experiment 2. So experiment 4 divided by experiment 2. So my rate for experiment 4 is 12. My rate for experiment 2 is 4. That's not confusing at all. So my rate is 12 divided by 4. As before, I've got a rate constant that I don't know what it is over itself. I have my A, which is going to be the same, that 0.2 to the X, because again, we already selected concentrations that are not changing. So experiment 2, the concentration is 0.2. Experiment 4, the concentration is 0.2. In B, the concentration of experiment 4 is 0.1. And you can see I'm just putting in still the exponents because again, if I was solving for this one first, I could actually still use them with all the exponents. I could go ahead and put my exponents in and solve for all those numbers. Either way will work. I know having multiple options to solve the same problem is usually not what you're looking for, but it's true. There are multiple ways to solve this problem. For C, 0.3 and 0.1. 0.3 to the Z power divided by 0.1 to the Z power. So as before, anything that's just 1 over itself is just 1. So I have 2 values of K, even though I still don't know what those are, they're just 1. My 0.2 to the X is over itself. My 0.1 to the Y is just over itself. All of those are 1. I am left with 3 equals 0.3 divided by 0.1, which is also 3, all raised to the Z power. So I am back to that ability of guess and check, where again, we'll just start with Z equals 1. And when Z equals 1, I would take 3 to the first power, and that in fact does get me 3, which is the correct answer here. So Z is just equal to 1, and I'm finished. The other way to do this, so this was the way to do it mathematically. The other way to do this was to just look at those rates. So I'm going to scroll back up and I have my red arrows. So I had a rate of 4 and a rate of 12. So, and I had a concentration of 0.1 and a concentration of 0.3. So my concentration tripled. My concentration went up by a factor of 3, and my rate also went up by a factor of 3. Since they went up by the same factor, that multiplying both of them by 3, that actually tells me that I have an overall exponent of 1, or that there's a linear relationship between the change in concentration of C and the changing of the rate. That is just a nice linear relationship. C changes, it triples. The rate also changes, it triples. A nice linear relationship. So my first goal was to find the rate law. I now know that X is equal to 0. So I can just go ahead and put a 0 in there. I also now know that I now know what Y and Z are. So I now also know that Y is 4, and I know that Z is 1. So now in my rate law, I can actually put in numbers for all of those exponents. I'm also going to go ahead and clean this up because there are some things when we write rate laws that we usually do. So when we write rate laws, as I mentioned as we were going through, because exponent of 0 means that it's not affected. Really, in my rate law, you're just not going to see A at all. So because my changing concentration of A does not affect my rate law, A just does not belong in the rate law at all. The other thing I'm going to erase is the number 1 by C, because that 1 is understood. So anything raised to the power of 1 is just itself. So we don't write in ones for exponent. The fact that the C is still present there in the rate law gives you that same information. So there is finding the rate law. My next thing says to find the value of the rate constant, K. I can take any one of these data points of these experiments and plug them in. For simplicity's sake, I am just going to plug in number 1. So my rate here is supposed to be 4. I'm going to be solving for K. My concentration of B is 0.1 raised to the 4th power. My concentration of C is 1. That basically means, so I've got 4 is equal to K. And then one of the things I do want you to notice is, while I can go ahead and put this in point, 4, that also means I now have molarity here to the 5th power. This 4 over here for my rate is in units of molarity per second. So when I solve for K, I want to solve for both the value, which is really kind of big. I'm going to write that in scientific notation just for funsies. Maybe not. So that is 400,000 or 4 times 10 to the 5th. It's a pretty big rate constant. But I also am going to divide by molarity to the 5th. So this also means I have molarity to the negative 4th power and my inverse seconds equal to my rate constant. So being able to think through not just the value of K, even though that was what the question asked for, but also the units are valuable. You have my apologies that I didn't write out the units of the rate as we went along, but they should be in molarity per second. Every once in a while, you'll see a rate done in molarity per minute or molarity per hour, but for the most part, you're going to see molarity per second. And it's just that time factor that would change. So there's my answer for number 2. And then last but not least, as for the overall reaction order. Overall reaction order just means we add up all the exponents. So for overall reaction order, all I really need to do is add 0 plus 4 plus 1 to get me a grand total of 5. So my overall reaction order for this reaction is 5. You might notice that that actually matches how many times my molarity was multiplied by itself. And that anytime you would have a 5th order reaction, you would in fact actually have these particular units of the rate constant, even if it came from different places. So that way we've at least done something out of the kinetics chapter. So in the few little bits of time I have left, one of the things I want to point out that we did not talk about, hanging out in your potentially useful information, there is this whole box over here on the right. You need to know what these equations are. You will need to use a lot of them for the exam on Saturday. One of the things I will be doing, so you might have noticed me scrolling over a wall of text, which were questions that my class asked. So I will be doing a follow-up video to answer some of their questions. And one of those questions was to basically go over all of the equations. I don't know if I can go over all of them, but I'll go over a lot of them. Including the fact that some of these you actually will not need, because one of the things on here is this equation, which is a 0 order reaction. We are only going to cover 1st order reactions and 2nd order reactions. The one that I just X'd out is a 0 or 0th order reaction. And we actually will not be covering that. But we went ahead and threw the equation on there anyway, just for fun. Also, we used to cover it, and maybe we will again in the future. So it's on there, but you won't need it because we're not going to cover it. Likewise, this here is the Arrhenius equation, which we will cover conceptually, but we will not actually cover calculation questions on it. This thing is not in the chapters we're covering. That's a chapter 15. No, 16. This is 16. Sorry, I had to think about that for a minute. That equation there is something that we will cover and you will need, but it's chapter 16, which is not on exam 1. You'll need that thing on exam 2. You don't actually need that thing right now. Same game with these guys down here. These are also exam 2 equations. So one of the things to be aware of is that while most of this potentially useful information is stuff that hopefully will look familiar, some of it is actually stuff that you guys don't need or won't need until later. So it is 5 o'clock. Are there other questions from the chat?
There's just one.
Okay.
Wait, sorry. I'm assuming does it matter what experiment we use to solve for C? Like if I want to do 3/4, would that be okay?
Yeah. So I will go ahead and address that one. So especially because C was the last thing that we solved for, and that way we had all of the other exponents, you can actually use any of them. So basically all you would have done is if you wanted to use 3 and 4, you would just, because C was solved for last, you already know that the concentration of A should be raised to the 0 power. We already knew by the time we got to C that the concentrations of B should have been raised to the 4th power. So you're absolutely right. You can actually, if whichever one you solve for last, you can use any of the experiments, because even though the trick that I kept using was, hey, it's just over itself, so it's just 1. But by the time we got to C, we actually had information that you can actually plug in and use. So no, you're absolutely welcome to use any experiments that you want when you're solving for the last one, because you have information about the other exponents. So yeah, no, that'll absolutely work, since you have information about the exponents. Cool. Anything else out of the chat before we sign off?
No, ma'am.
Fabulous. Then it is 5 o'clock. So I am aware that there were a variety of things out of the chat that I didn't get to, which includes looking at that graph again. So I am aware of that. That also came up in the questions that I asked my class for. So I will be making a follow-up video. I will be making a follow-up video. We did do freezing point depression. I will make up that follow-up video, however, tomorrow morning when I'm back in my office and am reunited with my Wacom tablet pencil. So it's coming, but it'll have to be tomorrow morning. So have a good night, y'all. Happy studying.
Thank you as always, Dr. Taylor.
Thank you.
Thank you.
So I will make that follow-up video and send that to y'all as well. But yeah, that won't be until tomorrow.
Okay, sounds good.
Yeah, have a good night.
Get the link. Thank you.
Have a great night.